So section 3.3 is derivatives of logarithmic and exponential functions. So the last two sections have been a lot of work to reaffirm our foundations of logarithmic and exponential functions, as well as extend into the ideas of limits of those functions. That's our first little bit of calculus involving them. But ultimately, we'd like to be able to differentiate the function of log base a of x, and ultimately we'd like to be able to differentiate the function a to the x, the exponential function. So we'll start with the logarithmic function, interestingly enough. So what we have is if f of x is equal to log base a of x, then of course a is greater than 1 or a is at least positive. Typically we use bases that are greater than 1, or we can convert, use change of base otherwise to fix them if they're not. But we can't have a logarithmic base that's not positive, so just keep that in mind. Nonetheless, this function is differentiable, and it has this as its derivative, 1 over x times log base a of e. Now keep in mind, this is just a constant. Log base a of e is not really anything particularly interesting. It's just some, whatever a is, it could be log base 2 of e or log base pi of e. Or if it was log base e, natural log of e, it would just be 1. And we'll see that momentarily. So where does this formula come from? This is a really nice derivation. We have to remember, as a couple sections ago, we saw the definition of e as a limit. It might be helpful to think of this as, let this be u, limit as u approaches 0 of 1 plus u to the 1 over u. That way we don't confuse it with our independent variable x down below. But nonetheless, as is, this is a true statement, no matter what the variable in the limit is. So this is going to come up. We're also going to use the fact that logarithmic functions are continuous, and that follows from the fact that they're the inverses of exponential functions, and exponential functions are continuous. And we saw previously that the inverse of a continuous function is also a continuous function. So the logarithms inherited that. Now, where we showed that exponential functions are continuous may or may not have been in the textbook or notes or previous video, but nonetheless, they are as well. So let's have at it. We're given that a is greater than 0. All right, we're just going to assume that right out of the gate. We're writing down that f of x is equal to log base a of x, and we want to find the derivative of this general logarithmic function. So f prime of x, by our definition, right? This is a derivative we've never calculated before, so we're going to have to go back to the definition in order to establish what this thing is, right? So that's the difference quotient here. And when we plug in for f, we have log base a of x plus h minus log base a of x over h. Right? So that's our explicit difference quotient now. Now remember that we have a difference rule for logarithms, or a quotient law for logarithms. The difference of two logs is the log of the ratio of their arguments, as follows in the next line. So log of x plus h over x is equal to that expression. So we use that log law kind of in reverse from how we're used to using it to get to this quotient. And the next thing I'll do is I'm going to move this division by h. I'm going to write it as 1 over h. And then I'm going to multiply by x over x. And I'm going to mix those terms up. So we'll kind of take this. Let's work backwards from this step right here. I can cancel x's if I wanted to. I don't want to. I've introduced them for a reason. But they would cancel. I have 1 over h is what would remain. And that would be times log of 1 plus h over x. Well, that's exactly what this is. Log a of x plus h over x all over h. There's our 1 over h in the denominator here, matching up with this 1 over h. And the x's that canceled, we wanted to go backwards. Inside here, I have x over x plus h over x. So I have 1 plus h over x. So the argument has changed in this step as well. Now I'm going to move this, since it's a product or a multiple of log base a, I'm going to move it into the exponent of log's argument. Remember, that's one of the other logarithmic laws that we've got available to us. 1 over x doesn't really matter. We're going to see that it doesn't even matter with respect to the limit because it's not an h. So I'm going to move it out in front of the limit as a multiple. So provided that this limit exists, it's 1 over x times the limit is equal to the limit of 1 over x times that function. So we're able to do this thanks to a limit law. Now, what do we have in this next step? 1 over x is moved out. We're taking the limit as h approaches 0 of log base a of 1 plus h over x to the power of x over h. And this is starting to look familiar. H is going to 0, so it's driving this term, 1 plus h over x, to 1, and it's driving the numerator to infinity. And that's exactly what we see above right here. X is going to 0. It's driving this term to 1, and it's driving the exponent to infinity. So we're starting to form this e within the limit. What we need to be able to do is apply the limit to this expression. Okay, so since log is continuous, remember that for a continuous function, the limit of a continuous function is the continuous function of the limit. All right, so now I can pass the limit through thanks to the fact that log is continuous. And now I'm able to apply the limit as h approaches 0 to this expression as is. And this really, at heart, is equal to e without doing any of the substitution. But if you want to understand it a little further, you might say, okay, well, let's let this be u, as we've done right here. Then we'll note that as as h approaches 0, u also approaches 0. Or to put that more concisely, u approaches 0 as h approaches 0. So we can swap this out to be a u approaching 0 instead of an h approaching 0. And we can swap h over x out as u and x over h out as 1 over u. Right? So, oops. Yeah, let me rewrite this. We don't quite have it down here. Let me clear this out of the way. If u is h over x, then of course 1 over u is the reciprocal of the other side, x over h. So there's all the pieces we'd like to see. And once we've done that, in this line right here, what we see is that we have exactly the expression up here. It's equal to the natural e, right? And of course, we can rewrite this as e then. Now, I guess there's an extra step. That's not really necessary. Nothing really happens in that step, of course. But what we see is that this component is e, the number e. This 1 over x just sits outside. The limit is evaluated once we swap that out for an e, and we have 1 over x times log base a of e. So there we go. Thanks with our definition of a limit of a derivative, for a derivative we've never seen before, we need to use the definition to calculate. And there we have, we've done it, and now we've confirmed that this formula is correct based on that definition. And now we're able to use this to calculate. Now we can start calculating the derivative of logarithmic functions. So we'll do that first, and then we'll start taking the derivative, or we'll derive the formula for the derivative of an exponential function. A couple quick facts. By the change of base formula, we can write the derivative of log base a of x, the function we just worked on, as follows: 1 over x natural log of a. Why does that work out? Well, remember that what we initially got was this on the previous page. It's from the box and from the derivation that we did. And if I want to use a change of base on log base a of e, and I want to change to natural log, I'll do natural log of e divided by natural log of a. Log base e of e divided by log base e of a. And that's exactly what's written here. 1 over x is just hanging out. And then I've got natural log of e, well, that's 1. E to the what power is equal to e? Well, e to the first power is equal to e. That's how we evaluate these logarithms. At least it's one way to think about evaluating them. So this ends up being 1 over x natural log of a as asserted right here. So that's a nice quick derivation of that. Now, if we take the derivative with respect to x of the natural log of x, well, interestingly enough, we just get 1 over x. Well, again, because this is 1 over natural log of the base. Well, in this case, the base is e, so 1 over natural log x times natural log of e, and this cancels simply to 1 over x. And this is the derivative we're going to see most often out of all of these, right? Because after all, if you were asked to take the derivative of a function log base a of x, and you didn't like the idea of doing that, you could always use a change of base formula to make it the natural log of x, and then 1 over log base a of e, right? Or whatever your change of base formula dictates. So nonetheless, this is the important one of all of them, the most important one, or the most used, I should say. Okay, so now let's apply this, right? So f of x is log base 5 of x cubed plus x. Find the derivative of this function. Differentiate all these functions. So f prime of x, I see an outer function, and that's my log base 5 of something, okay? And I know I have an inner function, so I'm going to use a chain rule when I work on this. So according to the rule up here, let's just stick with this one. It's kind of cleaner, right? And what we'll have is 1 over whatever is in the log's argument, in other words, this right here, times the natural log of the base. Well, the base is 5, so natural log of 5. So there's our outer derivative right there. Remember that we have to take the derivative of the inner function as well and multiply that. So here's our chain rule kicking in to take the derivative of this function, or we can look at it here. And that derivative is 3x squared plus 1. And that's exactly what we have here. Then we can rewrite this in the numerator as follows. And overall, our answer comes out to this. So there we have it. Now, another one, natural log of 1 over x. Okay, well, let's be careful here. This could look kind of confusing. Let's take our time with it. This is the natural log of x to the negative 1. There's another way to write this, right? Converting the fraction. We don't have to do it this way, but by doing it this way, I'm going to avoid the chain rule, right? So negative 1 times natural log of x is the result of the power law for logarithmic functions. So the exponent of the argument of log comes down as a multiple times log. So that's how that negative 1 moves down, the third log law. So then we're just looking at the derivative of negative natural log of x. So that's one really nice way to do it, because that's just going to be negative 1 over x, right? That line's not actually continued here. What I decided to do instead was, well, let's go ahead and do this as we see it, right? If we want to do this from this point, or maybe even from this point, then we can do that still, right? So the outer function, it's the derivative of the outer one, is 1 over whatever's in here, right? So we're starting here, derivative of this is 1 over whatever the argument is. So here's that, 1 over whatever the argument is. Then times the derivative of the inner function, derivative of 1 over x in this case. So the derivative of 1 over x, well, that's the derivative of x to the negative 1. Power rule says that's negative x times, or negative x to the negative 2, right? So that's this derivative. But over here, we have 1 over x, so that's just an x. So we have x times negative x to the negative 2, and that gives us, well, negative 1 over x. Now, that's not the easier way to do it. I just did it that way because maybe some students went that way, right? We could still use the chain rule here, but laws of logarithms are really handy here. And if we can simplify this first, we might as well, because of course, this thing is also equal to negative 1 times 1 over x is the derivative of natural log of x. There's a lot less work going this way, and we get the same result. But if you don't see it, you just use the chain rule and hopefully do that correctly. So the last one here, this is a little bit tedious maybe, but well, I'll start it at least. Y prime is equal to 1 over sine squared of x, right? The derivative of natural log of something is 1 over whatever's in the argument. And then times, the chain rule says take the derivative of that inner function. Well, that inner function is sine squared of x. Okay, well, that's also a chain rule derivative, right? We've got 1 over sine squared x here. And then that's times the outer function now is the square function. So we use a power rule, 2 times sine of x, or sine to the first of x. You don't really need that first power, it's just sine of x. And then we have times the derivative of, well, the inner function here was sine of x. So don't forget to take that one's derivative and multiply it. And I think we see by the time we're done with this, it's not too bad. We have a factor of sine cancel with a factor of sine squared here. And we'll end up with 2 over sine x. That's simplifying the first part. And the derivative of sine x is cosine x times cosine x. And then maybe we're savvy and we see that cosine x divided by sine x is cotangent x. And we have 2 cotangent x. It's a nice Nice move. If not, 2 cosine x over sine x is equivalent and probably fine for most purposes. So there we go. Derivatives with logarithms. Once we know how to differentiate a logarithm, chain rule, product rule, all these things are going to kick in and still be applicable. So let's take a look at something a little more interesting, right? It's going to be important to us to be able to take derivatives of this function, and later on we'll see moving in the other direction when we talk about the integral calculus. This is going to end up being a pretty important character in calculus to come. So let's just remember what the definition of the natural log of absolute value of x comes out to. We can split this up piecewise. It's natural log of negative x anytime x is less than 0, right? We have to correct the negativeness of this x value to make it positive by multiplying that negative number by this negative sign. Okay? If x is already positive, we do nothing. We just take natural log of that positive number. So if we're interested in f prime of x, well, we know that for x greater than 0, this is the easier case. So for this absolute value situation. Well, so if x is greater than 0, the natural log of absolute value of x is just the natural log of x. We're taking the derivative, just kind of held off doing that as we've gone through this step. And well, the derivative of natural log of x with respect to x is just 1 over x from our previous rule. So there's that one. If x is less than 0, what happens? Well, if x is less than 0, here's our expression. We're going to take the derivative of natural log of absolute value of x. Well, we interpret the absolute value of x to be negative x now. And that's okay. We're just going to run with this because we know that's positive because x is less than 0, so the minus sign corrects it to be positive. And now I just take the derivative. I'm going to use the chain rule, right? I'm going to have d dx, so it's 1 over whatever is in the argument of natural log. So that's 1 over negative x then. And then times the derivative of what's in the argument. So times the derivative of negative x. The derivative of negative x is just negative 1. So I have negative 1 over x times negative 1, so I get positive 1 over x. And what it turns out to be the case for us, quite nicely, is as long as x is not 0, then the natural log of the absolute value of x is equal to 1 over x. Oh, there we have it. And that's, again, for now, it just seems like a distraction, a little sideshow or whatever. But this will come in handy later on, in either later in this course and in calculus courses to come. So here's a use for, really nice use actually for logarithmic differentiation. And what this technique, this logarithmic differentiation is it's a nice method for handling derivatives of functions that have exponential situations going on, right? So if you have a trouble with an exponent and you're trying to take a derivative, oftentimes logarithmic differentiation is the answer. So what is the method of logarithmic differentiation? Well, take a natural log of both sides of an equation, y equals f of x, right? And this is presumably because f of x has a messy exponent that we're not sure how to deal with, or something unusual, maybe even. Right? And we use the laws of logarithms to simplify the result, whatever that's going to come out to. Next thing we'll do is differentiate both sides of that log equation with respect to x, because we can differentiate logs now. We know how to do that. Be sure to, we'll differentiate both implicitly and explicitly, right? For the function of x, well, that'll be just an explicit derivative. But don't forget, for the function of y, we take the derivative with respect to x, we're going to get an implicit derivative. And that's what's going to help us out because we'll have y prime floating around, and we'll just solve that resulting equation for y prime. Okay, so the steps, maybe they don't make sense until we actually start to do it, right? So we'll have a look at that in just a moment. So a very interesting fact is we never really proved the power rule for general real numbers n, right? This was back in 3.1, I believe. No, we talked about exponential functions in that case. But back in chapter 2, when we introduced the power rule, we just said, well, we're going to take it on faith that this works for all real numbers. We were able to convince ourselves it worked for all natural numbers, and maybe we were able to convince ourselves all rational numbers. But we certainly weren't able to prove that it was all real numbers at the time, even though we just accepted that as something we'll prove later on. Well, what turns out to be the case now is it is true for any real number as we've been using it, right? And the way we can prove that it's true for any real number is through logarithmic differentiation. So I'm going to start with this side of this identity that I want to prove, and I'm going to use logarithmic differentiation to help me do that. Okay, so I have y equals x to the n, and I'll take the log of both sides of this equation. I get natural log of y equals natural log of x to the n. And again, remember, we were only when we proved the power rule for derivatives, we use the binomial theorem in the expansion, the binomial expansion of x plus h to the n, right? And then we may or may not have done that in a live class meeting. We certainly didn't do it in a video, but it is in the textbook. Okay, so that binomial theorem only works when n is a positive integer. So just keep that in mind. This is what this technique is now solving for us. It's confirming that even though we didn't prove it for real numbers, this is actually true for real numbers, and what we took on faith was actually valid. So anyway, we're here, right? Remember, the laws of logarithms allow me to take this exponent of n, and I can bring it down as a multiple in this arrangement. So I simplified using the laws of logarithms to this expression. Now I'll take the derivative with respect to x of both sides. Well, on this side, the derivative of natural log of y is 1 over y dy dx. The implicit derivative is dy dx, right? Or y prime, if you like. Now on the other side, the derivative of n times natural log of x, well, that's just n times the derivative of natural log of x. Derivative of natural log of x with respect to x is 1 over x. And n is multiplied by that as a constant multiple. So now we're ready to solve for dy dx, in other words, for y prime. And that's the third step of this, right? So again, first is take logs, simplify. Second step, differentiate with respect to x on both sides. Third step, solve for y prime, or dy dx. So in order to do that, I multiply both sides by y, and I end up with y prime is equal to y times n times 1 over x. And this looks pretty good. I'm convinced that I'm more or less on the way. It's just, what is this y over here? We'll have to remember that y was x to the n. And that's what happens in this step. So y prime is n times x to the n times 1 over x. Well, that's x to the negative 1, right? So then x to the negative 1 times x to the n gives me x to the n minus 1. And there we have our power rule. And this, we can see, works out for any real number whatsoever for n, right? Even though we never really did prove that. Now we've actually officially established that result. So just a, not exactly the most practical example, actually probably more practical than all the other examples, but still abstract because we're proving something. Now let's take a derivative of a function that maybe we just find in the wild somewhere and need the derivative of. We're not confirming any rules or proving anything anymore. We're just going to calculate. So we have a real problem with this thing, right? Is it an exponential function or is it a power function? Well, you might say it's an exponential function because it's got an x in the exponent. On the other hand, you might say it's a power function because that has an x in the base. Well, it actually classifies or qualifies as neither, right? This is not a real number. That's not a real number, at least not a fixed real number. So it's neither a power function nor an exponential function. And the main problem is, well, it's an exponential expression that's hard to manage. You need to find the derivative of it. It's going to turn out that y is equal to x to the x. Take the natural log of both sides of this. On the left, we have natural log y. On the right, natural log of x to the x. Well, that exponent comes down as a multiple, and it's just x times natural log of x. So there's our simplification, right? Typically, what comes up most of the time when we use logarithmic differentiation, we talk about simplifying with a log law, we're talking about the third one, right? Because if we're solving a problem with an exponent, we're going to use the log law to bring down the exponent of the term inside the logarithm. So step 2, take the derivative with respect to x. d dx of natural log y equals d dx of x natural log x. Both sides of the equation we're taking the derivative of. Now we have 1 over y prime, or dy dx over here by the derivative. And this is always going to look the same every time. And that y be equal to this function and work from there. On the right-hand side, we have a product rule to handle. The derivative of x times natural log x plus x times the derivative of natural log of x. Find that all those terms match up once you work through the details. Now I've got natural log x plus x times 1 over x, and that simplifies to natural log x plus 1. But I need to solve for y prime, so the last thing I need to do is multiply both sides of this equation by y to solve for dy dx, or y prime. So I have dy dx is equal to y times natural log x plus 1, my expression from up here. And the last thing I do is I go back and I'm just going to reverse substitute, right? Y was equal to x to the x in the beginning, so I can get this derivative explicitly as a function of x. In other words, y becomes a function of x. And I have dy dx is equal to x to the x times natural log x plus 1. So there we go. That's the derivative of this strange-looking function. Right? And quite handily calculated too, right? That only took us 4 lines or so to get to that. So this is a really powerful technique for functions we would otherwise probably be quite a bit of trouble for trying to find the derivative. Okay, so let's extend on this logarithmic differentiation idea. One of the more important things it does for us is it allows us to calculate the derivative of an exponential function. So we're looking for d dx of a to the x. Okay, it turns out that's a to the x natural log a, but why? Let's see that, right? So remember that y equals a to the x. So I'm going to swap out my notation. Instead of f of x, I'm going to write y is equal to a to the x. And what I recall is that these two things are inverses of each other, right? So y equals a to the x is the same as log base a of y equals x. Sometimes it's easier to see it the other way. A to the power of x equals y. You sort of swing this around and it's equal to that, right? Sort of a counterclockwise view of things. It's written this way. Nonetheless, if I have this expression, I can take the derivative of both sides of this and then start looking for y prime, right? I can do that because y prime then will be the derivative of a to the x. So that's what I'll do. I'll take the derivative with respect to x of both sides, and I get over here d dx of this, d dx of x. Well, the one on the right is easy. Derivative of x with respect to x is 1. Derivative of this function with respect to x, well, that's going to be 1 over y natural log of a, right? That's from the formula a couple pages ago, this one right here, right? So just keep that in mind. You can go back and check it if you like, but that's from that rule. So there we are. I've lost my ability to get rid of my highlights here, but nonetheless, times the derivative of whatever's in the argument of log, and that's, well, just y, so that's dy dx. So now I solve for dy dx by multiplying both sides by y natural log of a, and I have dy dx is equal to y natural log of a. Well, what was y though? Well, y was a to the x, so this is a to the x times natural log of a, and that's our derivative of y, or our derivative of a to the x. And that confirms the theorem that's written up above here. Okay, so a couple quick calculations with it. Shouldn't be too hard to master this, but let's just see at least one or two. H of x is equal to 1 to the 10 to the 1 minus x squared. So what I've decided to do here is split this up into 2 different problems, right? I want to do, before I get too complicated and kind of lose track of things, so to see what would it look like if I took the derivative of 10 to the x here, right? Just to check. Well, the formula tells me that it's 10 to the x times natural log of 10. And that's exactly what I've written over here. 10 to the x natural log of 10. Okay, so that's what that's going to look like. We'll take a slower sort of sub-example before we launch into this bigger one. Because the bigger one, of course, has a chain rule. Our outer function is the exponential function, 10 to the power of something. But we have an inner function, 1 minus x squared, in that exponent. So now, the derivative of this function, the actual given one, is this. H prime of x, it's 10 to its power, right, times natural log of 10. So 10 to its power times natural log of 10. What we realize is that power, that inner function, by the chain rule, we need to take its derivative, multiply that derivative by everything. So it's no different than what we've done before. Outer functions done first, applied to the inner function. The natural log of 10 part is confusing. This is just a constant. Natural log of a, natural log of 10, just a constant, right? It doesn't have any exponent, any x variable or anything like that. So keep that in mind. It looks a little confusing, but you'll get used to it as you practice these. The derivative of 1 minus x squared with respect to x is 0 minus 2x. And this is just along for the ride, of course. And then so that's negative 2x times 10 to the 1 minus x squared natural log 10. All together, there's our expression. Now really, if I was being very thorough, I would realize that this is a constant. And I would move it over here, negative 2 natural log 10 times x to the 10 to the power of 1 minus x squared. Okay, so not terribly important, but by convention, it would be a little better to write it that way. So there it is. Again, the chain rule, product rules, all these things are appropriate with these exponential derivatives. Now, here's a nice fact, and this is probably one of our favorite calculus facts of all time. The derivative with respect to x of e to the x is equal to e to the x times the natural log of e, right? Where'd that come from? Well, it came from this formula. In this case, now we're talking about e in place of a. So we have e to the x natural log of e on the right, and that's exactly what's coming out of all of this, right? We see that natural log of e is just a 1. E to what equals e? Well, e to the first power is e. So e to the x times 1 is e to the x. So there we have our derivative of e to the x. It's just a fact that we'll generally remember from here forward, but it's nice to see where it comes from. And now they ask us to differentiate f of x equals e to the x over 1 minus e to the x, as well as another function down below that. So we have two different functions to find derivatives of, so we can go ahead and get to work on this, right? One way we might do this, you might say, I don't like the quotient rule, so I'll write this as e to the x times the denominator to the negative 1. And that would require a product rule and a chain rule, and maybe that's a worthwhile endeavor. But I think most people would just be happy to use the quotient rule on this thing. So we're just going to stick with that one, right? And that's what I do below. The derivative of the numerator, well, the derivative of e to the x, look above, is just e to the x. Fun to calculate with. We get e to the x times the numerator, 1 minus e to the x, minus the numerator times the derivative of the denominator. Well, the derivative of this denominator, be careful, is 0 minus e to the x. So just negative e to the x, as I have right here. That's 0 minus e to the x. Okay, so what comes out of all of this? Well, I've got some simplification to do. E to the x times 1. E to the x times negative e to the x. Negative e to the x times negative e to the x, right? So that's going to be a plus e to the 2x. So what I see here is e to the x minus e to the 2x plus e to the 2x. Remember, we add exponents when we multiply exponential expressions with like bases. And so we got e to the 2x. X plus x is 2x. These two added to 0, so they're canceling out. We have e to the x over 1 minus e to the x quantity squared. Oh, don't forget in the quotient rule that we square the denominator. Easy part, I just sort of skipped over that, but we finish up with this expression in the end. And we have that. Now, one below it. And this is sort of an out there kind of example. It's not connected to e to the x or anything like that. This is sort of just a test for students to try out, right? I could rewrite this as x to the 1/2 if I wanted to. And maybe I could start to see my way through this. The problem with this is, and resist the temptation, this is not an exponential function, right? This is not a constant base. So I can't apply this rule to it. right? A is some constant. It's not the variable x, right? It's not the variable we're taking the derivative with respect to. So this rule overall is useless to me. It was useless to me with x to the x. It's useless to me with x to the root x, right? Note that if this root x was maybe like square root of 2, then I could do just the power rule, and that would be just fine, right? But I can't use any of the exponential derivative rules, so I'll just put a question mark here and say, well, I'm not going to go that route. I don't want to make that mistake. What this thing ends up being is just sort of a sneak, and if you saw it and thought about it, great work. This is a sneak look at our sneak test for logarithmic differentiation again. We have a problematic exponential expression. Logarithms almost always do nice things for us here. So remember step 1, we've got this written as y. I'm going to take the natural log of both sides. And this is natural log x to the root x. I'm not worried about writing root x as x to the 1/2 yet, but I will want to do that in a moment. This is root x times the natural log of x. So there's a key step for us. Right. So I've introduced logarithms, and now I've simplified the logarithmic expressions. Step 2, take the derivative of both sides with respect to x. The left side with y, natural log y, that derivative is always this, 1 over y times y prime. On the right, maybe it's about time we wrote this as x to the 1/2 to help take the derivative. But notice that we have a product rule to handle here. So doing so, we get 1/2 x to the negative 1/2 times natural log x, derivative of first times second, plus first x to the 1/2 times derivative of second, the derivative of natural log of x is 1 over x. And some simplification here is in order. We'll do one more line of this to clean that up. We'll have 1 over 2 x to the negative 1/2 natural log x plus, or actually, yeah, plus x to the negative 1/2, right? This is x to the negative 1 times x to the 1/2. 1/2 minus 1 is negative 1/2. So there we have that. And then we're going to multiply both sides by y in order to solve for y prime. So then step 3 is y prime is equal to y times, just make a copy of all this other stuff here. And then right here. And what is y? Well, remember that y was x to the root x. So I can write that in as follows. We won't get any more simplifications out of this, but it's not bad to write it all in as is. X to the negative 1/2 natural log x plus x to the negative 1/2. And this is a perfectly sufficient answer, but something really interesting happens with this. You realize that x to the negative 1/2 is root x. So I could swap that out for a root x, right? So maybe I'll write that underneath. The root x is going to go there. Then I have 1/2 times natural log x. I can move that 1/2 into the power of x thanks to my log laws. So this is the natural log of root x, thanks to that. So natural log root x, thanks to the 1/2 moving in. And this is 1 over root x. So there is some nice simplification in the parentheses, and this is really not necessary for a test or, open answer where, I'm going to be a little bit more flexible with answers. But if you're checking your answer in the back of a book or something, it's nice to be able to convert this because you might see it written in this form instead. Natural log root x plus 1 over root x. Just interestingly enough, we can put all the roots back in, and that's just a mess of square root of x expressions. So that's out there. Either of these answers is fine. I'll box them both to emphasize that I was happy with the initial answer and would be on a test or quiz or anything like that. So there we go. That is derivatives of logarithms and exponential functions. So we are that's a big stride in calculus in general for us. Now we've got a whole other class of functions that we can differentiate. So the next thing we'll look forward to is differentiating inverse trigonometric functions and seeing all the interesting things that come out of those derivatives.